Let's say that you have a set of 2D points. You want to find the neighborhood of radius r of a point. You want to find all points within a distance of at most r. An obvious solution would be to just traverse all points and calculate the distance from each one of them to the point. This solution is fine for a single query, but if you're planning to perform multiple queries on multiple points, it may not be the best solution, because you'll have to traverse the whole set of points for each query, which can be millions or even billions. Let's discover another solution that is more time efficient. Let's assume that we have these points and our radius is 1. We can partition our 2D space as a grid, with each square having a side of 1. And you can see that we can easily know the square a point belongs to. For example, the point 4.65, 3.85 belongs to the cell 4, 3. We just calculate the Euclidean division of coordinates of the point by the radius. From that, we can have a pre-processing phase where we build a table mapping each square to the list of points it contains. Now let's say we want the neighbors of this point, points that are within a distance of at most 1. We can see that they can belong to one of the 9 squares around it only, not anywhere. So what do? We just traverse the 9 squares and check the points they contain. However, we can notice that not all the points in the 9 squares belong to the neighborhood. Some of them are in and some of them are not. This is why we need a second check by calculating the distance and keeping ones whose distance is smaller than or equal to r. And that's how we can find the neighborhood of a point with this new technique. The advantage over the previous technique is that even if we still need to check the distance, the number of tested points can be way smaller than the total number of points. It can be equal, but that's in the worst case. Also, know that here we use the radius of 1, but it works with any positive value of r. Let's implement this solution. Let's make a class neighborhood finder whose constructor takes as parameters the set of points and the radius. For the initialization, we build the grid map, a table that maps a cell to a list of points, ones that belong to that cell. To populate it, we traverse points xy and add each one of them to the cell it belongs to. To get the square our point xy belongs to, we just calculate floor x divided by r, floor y divided by r. They represent the row and the column in which the square is located respectively. Once we got the key, we add to its array our point xy. Now that we finished the pre-processing phase, we can have our query function, a function that takes as parameters the position of our query, qx, qy, the position whose we want to get the list of neighbors. We create the list that will contain our neighbors. We also need to find the keys of the 9 squares surrounding our point. Let's name the square of our point as x as y. Now, if our square is for example the square 2, 4, then we want to traverse these 9 squares. Squares whose indices are 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5, 3, 3, 3, 4, 3, 5. More generally, having as x and as y, we traverse squares as x plus I as y plus j, such that ij are couples in the cross product of -1, 0, 1 and -1, 0, 1. Basically the cross product of changes we apply to the row and to the column. We put the 9 values in a list. Now for each square, we traverse points xy that are located in that square by using the grid map we built during the pre-processing phase. And if the distance from our query point doesn't exceed r, the radius, we add the point xy to the list of neighbors of qx, qy. If it's not qx, qy itself, of course. Finally, we return the list of neighbors after the loop. And we solved our problem. What about the time efficiency? Is it better than the brute force solution? For the pre-processing phase, we traverse all the points. The time complexity is of n. But the advantage is that we do it only once, not at each query. And for the time required for one query, we're traversing the points present in each of the 9 squares. In the best case, we find no point except the query point itself, one point to traverse. And in the worst case, all points are contained in the 9 squares, which traverse all the endpoints. We can say that the time complexity is O of k, with k representing the number of points in the 9 squares. It can be between 1 and n. Basically, the time required for a query depends on the number of points around the query point, so it can be way faster than the brute force solution when we have a few points around. By the way, for finding neighbors of a point within a given radius, there exist methods other than the brute force one and the one we've seen in this lecture. We can for example use KD trees. Also, we applied our solution on 2-dimensional points, but what if we have 3-dimensional points, or k-dimensional points? If we take 3D points for example, the method works, but we need to traverse 27 cubes, 3 times 3 times 3, because points within a distance of at most r can be located in any of the 27 cubes around. Then with 4-dimensional points, we need to traverse 81 buckets, 3 times 3 times 3 times 3, and so on. You can see that the number of buckets to traverse is growing exponentially with the number of dimensions. We have 3 power d buckets to traverse, which makes this solution less efficient for higher dimensions. You should use it with points of low dimensions only, such as 2D and 3D. We've come to the end of this video. I hope that you learned something new. Tell me in comments if you did. Also, I released a course on graph algorithms. It contains 15 hours of content and covers more than 30 graph algorithms with explanation, examples, implementation, and more. The link is in the description. See you in the next one.